Welcome to Classes with Atish. In this episode, we will talk about a very simple but very interesting concept. Is the concept of linear momentum and conservation of linear momentum. So let us get started. Okay. So what is linear momentum? Linear momentum is defined as the mass of a body times its velocity. Okay. Since velocity is a vector quantity, linear momentum is also a vector quantity and it is denoted by a small p. Okay. Now from this, we can look at a few things. First up, we know force is defined as mass times acceleration according to Newton's second law. Okay. Now acceleration can be represented as rate of change of velocity. Okay. Now this term mass times change in velocity is nothing but change in momentum. So force can also be defined as rate of change of momentum of a body. Okay. Also, if we write force in this form, delta P, which is change in momentum over a period of time, then we can say F dot or F times delta T is change in momentum. Okay, there is a specific term for F times delta T. This is called impulse. Okay, so the impulse on a body is equal to the change in momentum. Okay, okay. Now again going back to Newton's second law. So the net force, net external force, let's write it down, net external force on a body is equal to the mass times acceleration of the body. Okay. Now, or we can say this is equal to change in momentum over a period of time. Okay. Now, if this is important, if net external force was equal to 0, okay, if net external force was equal to 0, then it follows that change in momentum is equal to 0. So whenever a system has maybe multiple forces acting on it, but the net force acting on the system, all external forces, is 0, then that system is called isolated system or also called closed system. So it means the same thing. If it mentions an isolated system or closed system, it means the net external force is all equal to 0. And if that's the case, then the change in momentum is 0. So what does that mean? That means momentum is of that system is a constant. Okay? So let me actually write it down. This is of the system, not of an individual part of the system, but of the system is constant. So what that would mean is momentum is conserved, is a constant over the entire duration. Okay, so we can write P initial is equal to P final. In fact, if I plot the momentum of the system versus time, where F net external is 0 over any period of time, this is a constant. It's a straight line. Okay? We can take any point as initial point and any point as final point. The momentum at any initial point or any final point will be 0. In fact, at all times between that chosen initial and final point is 0. It's a very important concept and very important to understand what's happening between the initial and final points that we are considering. Everywhere momentum is conserved. Okay? This is called conservation of linear momentum. Okay? So again, just to understand, just to restate that again, linear momentum is conserved only when the net external force is equal to 0. Okay? Now let us look at this as, let's consider any arbitrary system and see what exactly this means. Okay? Okay. Let us consider a system of masses. Let's say there is a mass m1, m2, m3, and like that mn. m1, m2, m3, mn. Okay? And each of these are at respective distances or displacements R1, R2, R3, and like that up until Rn. Okay? And we say that this system of masses exists. Okay? Now, what would be the center of mass of this system? So, our center of mass, RCM, will be M1 R1. So, these are all vectors. Okay? M1 R1 plus M2 R2 plus M3 R3, like that up until Mn Rn, okay, divided by M1 plus M2 plus M3 to Mn. Okay. So that is the center of mass. Now, if we differentiate this with respect to time, then we get the velocity of the center of mass, and what we get on this side is m1 times the velocity of mass m1, rate of change of its position. Like that, we'll get m2 v2 and mn vn divided by the sum of all the masses. Okay? Cool. Now notice something here. We just define momentum as the product of mass and velocity. So this can also be written as P1 plus P2 plus P3 all the way to Pn, and denominator we can also write this as the sum of all the masses. So let's say that total mass is m, where m is the sum of all the masses. Okay. Now we have the velocity of center of mass here. Now if I multiply this on the other side, so this becomes mvcm. We can just get rid of this. Okay. Now what is mvcm? This is momentum of the center of mass. Okay. So momentum of the center of mass is the vector sum of momentum of the individual discrete masses. If it was continuous, then we'll do an integral summation. Okay. Now, let us further look at this as, let's go back to this and let's differentiate this with respect to time one more time. So m, I will just put it that side, times derivative of VCM with respect to time will give us acceleration of center of mass. Okay, and that will be equal to mass times acceleration of the individual discrete masses which make up the system. Okay, sum of mn times acceleration of the nth mass. Okay, good so far. Now what is this? Total mass times acceleration of the center of mass. That is nothing but the total external force acting on the system. Okay, good. Now let's say if total external force acting on a system is 0, then from that what we can infer? We can infer that acceleration of center of mass is 0. Okay, but it does not mean that the individual accelerations of the discrete masses that make up the system is 0. It does not mean a1, a2, a3, an, they may not be 0. Now if acceleration of center of mass is 0, then from that we can infer that velocity of center of mass is a constant, not 0, constant, right? So if there is no external force, the velocity of center of mass remains constant, which means if I multiply m, the total mass of the system, times VCM, that is also a constant, which means what? The momentum of the center of mass is a constant. Okay, PCM is a constant. Okay, so what that means is whatever the momentum of the center of mass was in the initial state will be equal to the momentum of the center of mass in the final state. Okay, so that is again the law of conservation of momentum, but the thing here, this explains it a lot better because this shows us that when we say there is no external force acting on a system, it means the momentum of the center of mass is a constant. It may not mean that each of the constituent momentums of the discrete masses making up the system is a constant. Their vector sum is a constant. Okay, so This means vector sum of P1 plus P2 all the way to Pn is a constant. Okay? So if there were, let's just simplify this, if there were just two bodies, okay, if there were just two bodies, let's say mass m1 and mass m2, okay, and this was moving with velocity v1, this was moving with velocity v2, okay, and something happened, there was no external forces, something happened, maybe they collided and its final velocity became v dashed 1 and m2's final velocity became v dashed 2. In that case, the initial momentum of the system was m1 v1 plus m2 v2. This was what? Initial momentum. Okay? This will be equal to m1 v1 dash plus m2 v2 dash. This is what? Final momentum of the system. And this is applicable only if the net external force was 0. Okay? So that is what it means by conservation of linear momentum. Now, without an external force, how is it possible that maybe a mass changes velocity? Multiple things could happen. Maybe there was a collision, or maybe we can look at different questions now. There could also be a situation that maybe you are standing on a trolley, okay? This is M1, the trolley is M2. If you start moving this way, there is no net external force. What will happen? The trolley will move the opposite way to conserve linear momentum. Okay, it's very interesting problems. We'll do some examples and this will become much more clear. Okay, let us suppose we have a gun, okay, and someone pulls the trigger. The gun mass is M, capital M, and someone pulls the trigger and a bullet whose mass is small m is shot out of the gun with velocity v1. Okay? Find the recoil speed of the gun. Okay? First thing is, when we pull a trigger in the x direction, because we are only concerned with what is happening in the x direction. First thing is, can we say that net external force is 0 in the x direction? Yes, that's true. Not in the y direction, because y direction we have external force. Gravity is an external force. But let's just consider in one dimension. Okay, external force is 0. Now, if the net external force is 0, then momentum is conserved. So P of the system, here our system is the gun and the bullet together, is conserved, is constant. So therefore, we can write Pi, initial momentum, should be equals to the final momentum. Okay. Now, initially the gun was at rest. So initial momentum is 0. The final momentum of the system, so what is compressed of the system? The bullet and the gun. So let's look at the bullet first. its velocity is mv1 if we are taking the direction this side as positive. Let's say the mass, the gun recoils backward with velocity v2. Okay, so then this will be the momentum of the gun will be capital M v2. Okay, so then from here we can say that v2 is mv1 divided by capital M. Okay, so it's a very simple problem, but really understand how to apply the law of conservation of momentum and when to apply. Okay, this condition is absolutely critical, that the net external forces should be 0. Okay, now let's suppose there is a trolley. I was talking about trolley a little while back, so here we are. Okay, so there is a trolley which is on a frictionless surface, and there is a person. Okay, this person weighs, let's say, 50 kg, and the trolley weighs 100 kg. Okay, initially they were both at rest. The person starts walking on the trolley with speed 2 meters per second with respect to the trolley. Find the speed of trolley. Yeah, so basically find the speed of trolley. Okay, how will we solve this problem? Now, first thing, again, take a look and see if there is any external force in the x direction. Okay, there is no external force. The man started walking, so whatever force you would have given on the trolley would have given an equal and opposite force on the man. So that's the reason the man is able to walk, and that's the reason the trolley goes back. But there is no external force. That's an action-reaction pair based on Newton's third law, and it's all internal forces. So great. So we have this situation, F external is 0. So if F external is 0, then momentum must be conserved. So momentum of the system should be constant. So therefore, P initial should be equal to P final. Perfect. Now, what's the initial momentum? Everyone was at rest, so it's 0. Now, what is the final momentum? Okay. Now, it says the man starts walking with speed 2 meters per second, but read the question very carefully. It says with respect to the trolley. When we have to find the speed of the trolley, we have to find the speed of the trolley with respect to ground. So we cannot use this 2 meters per second as is. We have to convert this speed of the person with respect to ground. We cannot just take 2 meters per second because it is the speed with respect to the trolley. So let's say velocity of man with respect to ground, this will be equal to velocity of man with respect to trolley plus velocity of trolley with respect to ground. Simple vector algebra. Now we know the velocity of man with respect to trolley, and we have to find the velocity of the trolley with respect to ground. Let's say velocity of the trolley with respect to ground is v in the opposite direction. Okay, so the velocity of man with respect to ground becomes 2 because this is in the opposite direction, minus v. You can also visualize it like this. If you were standing on the ground somewhere here and watching the thing happening, so as the trolley moves back, okay, after a while, the man has moved forward, but he has not moved as much forward as he would have if the trolley was stationary. So that's the reason his speed, his relative speed with respect to ground appears to be smaller than his speed with respect to the trolley. Okay? All right. So now that we have that, so let's look at forming our equation here. So momentum, final momentum, let's look at the man's momentum. So his weight is 50 kg. Okay, and he is moving forward with 2 minus v with respect to ground, plus, now what is the momentum of the trolley? The trolley is moving back, it is 100 kg, it is moving back with respect to ground with velocity v, so this must be minus. Okay, so then we can cancel this and make it 2. So 2 minus v minus 2v, or 3v is equal to 2, or v is equal to 2 by 3, or 0.67, the units are meter per second. Okay. This is the last problem we'll solve, part of this video, and then we'll close out. So this will be an interesting problem. Okay. This is a block. This is only quarter of a circle. Okay. And this quarter circle's radius, let's say, is r. Okay. This block, it sits on a frictionless surface. So this is frictionless. And then there is a mass m, which is dropped or let go from the top of the quarter circle. This surface is also frictionless. Okay. The mass of this block is 10 m. Okay. Now obviously this block will slide here. It will come here after a while with some velocity v. Find this velocity v, find v just before m leaves the big block. Okay. Now, first of all, let's look at what are the forces that are acting on mass m. Mg, which is the force due to gravity in the downward direction. There is, like, anywhere on the path, there is a normal reaction. Okay. There is no friction, so there is no frictional force. So this is for the small mass m. For the block also has force due to gravity, and then there is a reaction of this n in the opposite direction. Like if the block gives a normal reaction to small m, the small m also gives equal and opposite normal reaction to the big block M. And then there is no friction, so these are the only two forces that are acting on each of these masses. Okay. Now, normal reaction N for the system, N is an internal force. Okay. So we can ignore N. Okay. Mg is an external force. So can we use the situation where we can say F external is 0, therefore P is conserved, is constant. So we can use conservation of linear momentum? I don't think so, because we do have an external force here. But think about this carefully. If we choose our coordinate system as this as x and this as y, okay, momentum is a vector quantity. We can actually look at, is F external in the x direction 0? Yes, it is, because mg is acting in the y direction. So if it is 0, then we can say px is constant. Right? So momentum in the x direction is conserved. Not necessarily in the y direction, but in the x direction it's conserved. So we can use that. Okay? So let's do that. So let's assume when the block reaches here, its velocity is v. So for the system, initial momentum in the x direction is equal to final momentum in the x direction. Now initial momentum, I'm considering the case when the mass was here. In the x direction still it was let go, everything was stationary. So momentum for this mass as well as 10m was 0. Now when it leaves the block here, small m has a velocity v in the positive direction, and let's say this 10m will go back with a velocity, let's say u, in the opposite direction. So this will be minus 10m times u. So we get one equation here, 10 mu equals mv. We can eliminate the m's. So 10u equals v. We get one equation. Okay. So this is from conservation of linear momentum in x direction. Okay. Now let's look at something else. Now in the y direction we can't use conservation of linear momentum, but we can probably use something else. We can use work energy theorem. How can we use that? We can say, again for the system, work done by all forces is equal to the change in kinetic energy. Now what are all the forces that are acting on m and 10m? We can see that it's right here. So work done by gravity plus work done by normal reaction should be equal to the change in kinetic energy of the system. Now, what is the work done by gravity? The small m comes down by a distance r, right? The force of gravity is downward, the displacement is downward. So work done by small m is mgr. Is there any work done by 10m? 10m did move sideways, but its center of mass remained at the same height, whatever it was. If it was the geometric center, somewhere, maybe it was here, it will remain at the same height. So there is no work done by gravity on 10m. Cool? Now let's look at work done by normal reaction. Now normal reaction is perpendicular to displacement all the time for small m. So for small m it's 0. Normal reaction for 10m, I think the work done by normal reaction will also be 0 for both the masses. And then we look at the change in kinetic energy. So the change in kinetic energy, both were at rest in initial position, and small m's kinetic energy is mv square, half mv square, and 10m's kinetic energy is half 10m into u square. Although u is in the other direction, doesn't matter, squared of that will be positive. Okay, so we can write mgr equals half mv square plus 5mu square. We can cancel out the m's. Let's say we write 2gr equals v square plus 10u square. Now we have two equations. We can substitute v square in here. So maybe I'll just write it with here 2gr equals v square is 100u square plus 10u square, or 110u square 2gr. So u becomes gr by 55 root over that. So if we have u, v is 10u, so 10 root gr by 55. Okay? Okay. In the next episode, we will look at few other cases of conservation of linear momentum, specifically when a bomb explodes or a shell explodes. In that scenario, how linear momentum is conserved. And another interesting topic that we'll go over is the case of elastic and non-elastic collisions. So stay tuned. See you in the next episode. Cheers.